Hi everyone, my name is Jaskaran. I'm a PhD student in the Robotics Institute at Carnegie Mellon. This presentation is on my paper called Feasible Region-Based System Identification Using Duality. So this is the outline of this presentation. We will revisit the slide every now and then just to remind ourselves where we are. So what is the motivation of our work? Multi-robot systems have been used for many tasks, such as search and rescue, exploration, and coverage. Synthesizing controllers for these tasks is a forward problem, and it has been relatively well studied. On the other hand, the inverse problem, that is task inference, has not been explored as much in the context of multi-robot systems. Observer-based inference has several applications. For example, our observer could be another robot team, and here the question becomes, how can this team learn by imitating an expert team? Alternatively, our observer could be an adversarial team, and here the question becomes how easy it is for the observer to reverse engineer the task being performed by the team being watched. So the research we did in this paper is an attempt to answer those questions. So here are the main contributions of our work. Firstly, we propose a task inference problem that is suited for inferring parameters of optimization-based controllers that are used in multi-robot systems. Secondly, we develop a new set-based identifier that generates correct by construction sets that monotonically converge to the true parameters. Finally, we perform simulations to infer goal locations of robots in a multi-robot system. We demonstrate the benefit of our technique over UKF in terms of predicting valid goals always, and additionally converging to the true goal much faster than the UKF. So first, let us look at the forward problem being solved by the multi-robot system. Here's the setup. We have n robots in the system. Let's just focus on one robot, that is robot I. This robot must find a control UI to finish a task parameterized by theta I while avoiding collisions with every other robot. Let's assume that there is a user-prescribed nominal control for each robot called UI cap, and we take it as a given that this control by itself guarantees completion of the task parameterized by theta I. For ensuring safety, a linear constraint on the control has been proposed previously, which guarantees a margin of at least d sub s between every pair of robots. To mediate between the task completion and safety requirements, a quadratic program is developed which computes a control that is closest to the task-based control subject to the safety constraints. So in the multi-robot system, each robot I will locally solve this QP for its optimal control U-stop. Going forward, we will assume that the robots are using this optimization as the underlying control synthesis module. So now that we have seen the task-based safe control synthesis algorithm, let us come to the main topic of the paper, that is task inference. The task inference problem requires us to develop an online algorithm to estimate the underlying task parameter theta I by using the positions and velocities of each robot measured over some time. I want to distinguish between two types of approaches that can be used for doing inference. The first one is point-wise identification. This approach generates a single estimate of the parameter called theta cap, and the hope is that this estimate will converge to the true parameter as the algorithm gathers more data from the robot's motion. An unscented Kalman filter, or a UKF, is an example of such an approach. The other one is set-based identification. This approach will generate compact polytopes in the parameter space, and the hope is that these polytopes will converge to the true parameter as the algorithm gathers data from the robot's motion. This second approach is the focus of our paper. So let me give you a preview of what set-based identification looks like. Here we have a robot that is navigating among obstacles to reach its goal, that is x sub d, and the observer must infer the location of the goal by monitoring the robot and the positions of the obstacles. As you can see, our proposed set-based approach generates these green regions which do indeed converge to the true goal as the robot moves. So now let's look at the core formalism of our inference approach. Recall that each robot in the system solves this optimization problem to find its optimal control UI star. Now the observer knows that the robots are solving this problem, but the observer does not know theta I. To get a characterization of theta I, an explicit relation between the parameters theta I and the control UI star would go a long way. But since this optimization problem is inequality constrained, the relation between the optimizer UI star and the parameters theta I is rather implicit. The KKT conditions of this problem will help us get an explicit relation by converting this problem to an equality constraint one. So what are these conditions? There's stationarity, then there's primal feasibility, there's dual feasibility, and complementary slackness. So using these conditions, we can define the set of active and inactive constraints as follows. The set of active constraints is the set of all those indices, or robots in our case, for which the constraint is active, that is, equality holds. Likewise, the set of inactive constraints is those indices for which strict inequality holds. Intuitively, active constraints refer to those remaining robots or obstacles that the ego robot worries about for collision. An observer can easily figure out which constraints are active by just measuring the positions and velocities of the robots. Now, given these sets, the observer can pose an equality constraint problem as follows. So now we have two problems. The first one was the problem that each robot is solving. This problem has inequality constraints for collision avoidance with respect to every other robot in the system. Next, we have the observer's guess of the robot's problem, where we have equality constraints with respect to robots only in the active set. By way of our construction, both these problems will give the same control UI star for same positions of the robots. But it is this second problem that will help us get the explicit relation between the control UI star and the parameters theta I that we are after. So given this problem, we can derive this relation by looking at 5 possible cases. In the presentation, I will only discuss 3 to convey the idea. More information can be found in the paper. And these cases are based on the number of active collision avoidance constraints, that is the number of rows in A subactive, and the rank of this matrix. Note that case C involves more than 2 full rank active interactions, and for this case, point-wise identification will be unsuccessful. We will show why this is so later. But set-based identification will work for all the cases. So let's start by deriving a relation between theta sub I and UI star for case A. In this case, there is no active collision avoidance constraint. So the ego robot is free to use the reference control UI cap itself without worrying about collisions with any other robot. That is to say that the optimal control U star is U cap itself. But U cap is nothing but C times theta plus D, where theta is the only thing that is unknown to the observer. Now recall from the definition of inactive set that A sub j transpose U star is less than B sub j for all j in the inactive set. Therefore, substituting U cap theta in this equation gives us a polyhedral representation of the set where theta must belong. Now this set is time varying because the robots are moving, but theta will always be contained in the set as long as no obstacle is active. So at every time instant, we will get a different polytope in which theta is contained. Now, even though the shapes of these polytopes are changing with time, theta is time invariant. Therefore, theta will always be contained in the intersection of these polytopes over time. Using this fact, we define a set S of t as the intersection of all polytopes recorded until time t. The volume of S of t is non-increasing by construction, and therefore it represents a non-expanding set that is containing theta. Now let's come to the case B, where we have just one active constraint. For this case, we can compute an SPD of the active constraint to derive an analytical expression for U star, which is shown here. Finally, substituting for U cap in here gives us a closed form relation between the parameter theta and the optimal control U star that we wanted. Additionally, for this case, we can also derive the Lagrange multiplier for the active constraint in closed form as shown here. Now, just like for case A, we can use the definition of inactive constraints to compute a time-varying polyhedron where theta must belong. However, we can use one more piece of information from dual feasibility, that is the non-negativity of Lagrange multiplier. This gives us another time-varying polyhedron where theta belongs. Finally, we take intersection of these two polytopes and then take the intersection of these polytopes over time to get contracting sets where theta belongs by construction. Here's a simulation where we have a robot navigating to a goal x sub d, and the observer will try to infer the location of the robot's goal by watching this robot move. Obstacle number 2 is the single obstacle that remains active during the robot's motion. Using the sets proposed in the previous slide, the observer computes these green regions where the goal must belong, and correctly so, the true goal does lie in this region. Finally, we come to case C, where there are two full-rank active interactions. When a subactive matrix is full rank, the control is entirely determined by the active constraints. This is because both degrees of freedom in the control are exhausted in satisfying collision avoidance constraints. So in this case, the control UI star does not contain any information about the parameter theta. This also applies when there are more than two full-rank active interactions. Now, this is the reason why pointwise identification fails for this case. The Lagrange multipliers do depend on theta, and the non-negativity does give us a time-varying polyhedron in which theta belongs. In this video, you will notice that as the robot moves, two obstacles always remain active for some time. And during this time, the UKF-based estimate of the goal doesn't change at all. But a set-based estimate does correctly identify a green region which does enclose the true goal. As the robot exits this field of two active obstacles, UKF estimate quickly converges to the true goal, as does our green region-based estimate. Finally, let me show you some results for goal inference in a multi-robot system. In this video, the inferred goal regions are highlighted in the same color as the color of the robot. Let's just focus on this pink robot. As you can see, this is the region of the pink robot's goal. The UKF-based estimate takes longer to converge to the goal of the pink robot, whereas the region has narrowed down around the goal of the pink robot quickly. The UKF estimate is still here, whereas the region-based estimate has already triangulated the goal pretty accurately. With that, let's see the summary of our work now. So in this paper, we derived a set-based estimation algorithm for inferring task parameters of multi-robot system by using tools from duality theory. We demonstrated that this algorithm converges much faster to the true parameters than the UKF algorithm. In future, we plan to develop a robust algorithm to infer task parameters under uncertainty in positions and controls. And we also want to develop an algorithm for simultaneous inference of task parameters and constraint parameters. And with that, I'd like to thank you for listening to my presentation. Please feel free to reach out to me for any questions, and have a nice day.